Hi, I'm Mark Hamilton, and I'm a PhD student at MIT and a research development engineer at Microsoft. Today I want to share with you this project we call Large-Scale Intelligent Microservices, or ways to take any database and enrich them with cloud or containerized intelligence via Apache Spark. At its heart, the core of our project is to take large-scale databases with terabytes of data and make it easy to apply cloud or containerized machine learning to this data. What's difficult is kind of when you start to unpack this very simple diagram and really think about how to implement this. Underneath the hood of the machine learning component, you have a ton of different algorithms, most of which require specialized hardware like GPUs or FPGAs. This hardware doesn't come cheap, so often you want to share these algorithms across multiple different applications, requiring something like an elastic multi-tenant deployment. Furthermore, these algorithms are written in all sorts of languages like PyTorch or Flux.jl. There's tons of different ways to create modern machine learning methods. And some of these, like search or image search or web search, they even require the internet. So the idea of being able to take this and compile it down into a neat little thing and put it inside of your database is sort of naive and very difficult to work with. On the other side of the equation, databases aren't that so simple either, because there's a whole lot of them, and each one of them has a very particular way of working with it, a particular language and set of abstractions that it's used to. And a lot of things, they don't even have a compute layer, like Azure Storage or S3. These are sort of data stores, but not quite databases. So, what we really want to do is find some solution that works in all of these different cases. And unlike standard Microsoft products, we don't want it to look like this. We want a nice, simple solution that doesn't require making connectors for every single pair of these things in the ecosystem. So to tame this potential mess of an architecture, what we need to do is first tame the databases side, and for that we use Apache Spark. It's a fault-tolerant, distributed computing library that's elastically scalable, combines SQL and MapReduce style computations, has APIs for batch and streaming, and has wide language support. But the most important thing, and the reason why we want to use it, is that they have a unified data access API. So no matter where you get your data from, be it storage or Kafka or S3 or MongoDB, everything comes into Spark looking like a data frame that can be worked with in a distributed setting. So this provides a nice standard way to work with data in all these different locations. Given that our architecture really leverages Spark as one of the workhorses, it's worth taking a little time to understand what Apache Spark does. So here's a very simple scenario. We have a large CSV that's stored in cloud storage. We have a Spark cluster with 3 worker nodes and a driver node. Each one of the workers will split up this CSV into chunks called partitions, which is kind of an atomic unit of work that the Spark cluster can churn through. The workers will then lazily read these partitions as needed in order to perform the computation. And to the user, it just looks like you're manipulating a data frame. You don't actually have to get into the splitting or the reading or the distributed implementation of this. It's all taken care of by the Spark API. And what you're left with is a nice data frame API that you can do queries on and things like this at a much higher level, but still have the power of the Spark cluster at your disposal. So now if we come back to our original dilemma, this left-hand side is much simpler because we have a unified API over all the different kinds of databases that are out there, which is Apache Spark. Now to unify the right-hand side, to kind of come up with a good abstraction for all these different machine learning frameworks that support all these different kinds of restrictions you have under the hood in exotic hardware, we really are left with only one option, which is services. Or to compartmentalize all of these algorithms into an abstraction layer and communicate with it as opposed to actually running it. So that's the core abstraction that we use for this work. So now the problem really becomes how to create an integration between Apache Spark and web services. And to this end, we present HTTP on Spark, which is a deep integration of the entire HTTP protocol with Apache Spark. So this allows you to take your Spark cluster and harness it for massively distributed web serving and web client workloads. So we introduced these new primitives for working with web services. This works with a web service, a containerized service, or local services. So you really have a lot of options when it comes to your architectures. And it automatically figures out kind of the schema and parses things to and from that nice data frame API. So you can do this computation and stay tabular, not actually have to drop down to JSON if you don't need to. Web client workloads are not your standard bread and butter Spark kinds of computations. The one key difference is that when you're communicating with a web service, there's a lot of downtime. You send it some data and you wait for a response. And in that time, your thread isn't actually doing anything. So if you want to really get the most throughput, the most bang for your buck out of this kind of a system, you need to layer this computation asynchronously. You need to allow each thread to send multiple requests before waiting on the first one. And so this is a new feature that we add to Apache Spark, the ability to do asynchronous computation in a way that does not mess up Spark's parallelism. So in particular, each thread can multitask, can send out multiple requests at a single time, but this does not interfere with Spark's organization of the threads or of the worker nodes. So you really get all the different kinds of parallelism. You get machine level parallelism, thread level parallelism, and also asynchronous concurrency. So what we find is that this really can give you a boost of an order of magnitude without actually changing your computational footprint, just because you can more efficiently send data to these web services. And really with this, we're able to achieve performances that are much better than if you were to do something like this naively, even using Spark under the covers. So now that we have a system that can integrate Spark with any HTTP web service, we can bring on the machine learning services. We can add a whole bunch to our system. And thankfully, Microsoft has a whole bunch of these called the Azure Cognitive Services. And they really do everything from vision and entity recognition and language to searching knowledge bases and searching the web. So there's a huge variety of these different algorithms up there that are constantly being updated. And so these are just a few, and this is even an outdated list. So the key idea is that we now, with this architecture of HTTP on Spark, we add another layer which allows you to call all the different Microsoft intelligence services. And this is what we call the cognitive services for big data. So the basic architecture is that we create SparkML transformers that's able to take your data and coerce it down to the HTTP structure, send it off to the cognitive services, and then coerce it back to the structure that you care about. So it allows you to really easily transform terabytes of data without training or deploying your own model. You just point it at the cognitive service endpoint, and you can stick this into your existing Spark pipelines. And it's available on Python, Scala, Java, and R. And so this is kind of what it looks like, where you can create a simple text sentiment transformer, point it at a column of text, and very quickly get the sentiment of every single sentence in your data frame. So it's only a few lines. So anyone who's worked with a web service before can probably tell you that it's a lot more complicated to work with one of these things than you might ordinarily think. Often they have a huge number of different parameters and a huge number of defaults and different buttons and dials that you can tweak in order to change your computation. So what we really wanted to do is allow for the full flexibility, the full breadth of queries, but keep it simple for the simple examples and allow that complexity to scale with your complexity of the query. So the idea is that we've created a new Fluent API for orchestrating these kinds of services and parameterizing them in a flexible way. So this is a particularly simple one. We can take a Bing image search transformer and we can ask it to do an image search on each one of these queries. So we can set our query parameter, set it to a column, which is the name queries. And this will parameterize a large batch of web service calls, one for each one of these particular queries. But you might not want to parallelize over just all these different query words. You might want to page into a single query. So this is now a variation on the kinds of distributed query you want to do. In this case, let's say you wanted to get the first 500 results for a search term like cats. Instead of setting the query with a data frame column, you can set the query with a single value, in this case cats, and you set the offset, the depth that you page into with the column now. So you can now parallelize over the offsets of your calls. And this really scales to any combination of the parameters. So say you wanted to do something really complicated, you wanted to gather a variable number of queries for a variable number of terms and parallelize this across multiple different cognitive service subscriptions to make something like a multi-tenant service. This is again still a four-liner here. We can just parameterize each one of these query parameters with a column of our data frame to achieve this kind of more complicated orchestration scenario. And so with this, the initialization of your objects is on par in terms of complexity with your actual query. Our first application of this work is an effort in snow leopard monitoring, with the goal of tracking and identifying the endangered snow leopard population through camera trap images, just photos of a snow leopard that are taken in the wilderness. So to do this, we first kind of gather our data set. We pull a bunch of labeled data from Azure Storage. We can also use Bing Image Search to bootstrap a data set. We can search for snow leopards and gather a huge amount of images right off the bat without any human labeling. We can then train a deep network with TensorFlow on Spark and interpret this deep network to get a deep semantic segmentation method using Lime on Spark. Finally, we can push all of these results out to Power BI, a dashboarding tool, in order to create a real-time snow leopard dashboard that's currently used by the Snow Leopard Trust. This allows researchers to discover new areas of snow leopard density and to track leopards across the ecosystem to get a better understanding of their biology and their conservation status. Our second application is one for real-time race analytics. The idea is that we have a large stream of driver audio and telemetry coming from 50 cars at sub-second intervals from NASCAR. We then take the driver telemetry stream and run cloud-based anomaly detection on it. We take all of the live streaming audio and we pump it through the speech-text algorithms in parallel. Finally, we push these results out to Azure Search to make it easy to search through all of this different driver audio, and Azure Storage to hold the underlying raw data files. And from this, we can create visualizations, create front ends that allow race technicians to track the progress of the race and understand what's going on, and even hear out the competition to see what they're talking about. The final application is one in intelligent art search. The basic idea is that we have a large amount, around 500,000 artworks from the Metropolitan Museum of Art stored in storage. We can pump these through all the different vision algorithms like object detection, image captioning, content moderation, face recognition and detection. And finally, we can push these into Azure Search to allow a search interface that not only keys on the data that was provided by the Metropolitan Museum of Art, but actually understands the objects in the images and understands a lot more about the images than just provided by the curatorial description. So this is actually a live demo. You can check it out at gen.studio, and you can also play with a GAN to help you explore the collection as well. Now, with some of these examples, I know what you might be thinking. Isn't the network a bottleneck? Doesn't the speed of the network really affect your throughput when it comes to orchestrating large amounts of web services? And that can be true. When you're both dealing in the cloud, when you have your client and your server in the cloud, that can significantly help. But often, if you have a huge amount of data, you might not want to pump this through the cloud. You might want to have a more optimal solution. And so for this, in addition to our web Spark-based architecture, we also have a containerized architecture that takes all of these cognitive services, puts them in containers, and allows you to put these containers directly next to the Spark workers using a container orchestration system like Kubernetes. So now, using the same HTTP on Spark, instead of pointing this to the web service, we can point this to the local containerized services to enrich the cluster with intelligent algorithms in a modular and independently scalable way, and avoid most of the networking, because this call will just be a local service call. Data won't leave the machine, and will just be moved from one process to another process. So with this, we found that this can really make the difference for a lot of services, especially if the computation time is really dominated by the sending and receiving of data. So we found that in certain circumstances, you can get about an order of magnitude speed up in terms of your latency, and you can also dramatically increase your throughput as well. Finally, in addition to this, we've also undertaken an effort to show that these cognitive services are not just fast and easy to integrate with your databases, but also high quality compared to the competitors. So you can check out our paper for full details on our benchmarking effort, but this will be the first in the literature to systematically compare large cloud intelligent service providers across standard data sets. So we investigate image, content moderation, anomaly detection, sentiment analysis, and a whole bunch more. You can check out the paper for more details. So all of the work that I've talked about today is available in the open source as part of Microsoft Machine Learning for Apache Spark. This effort includes a wide array of distributed machine learning algorithms, fast model deployment system, microservice orchestration, which was the content of this talk, as well as a multilingual binding generation system. This is how we take HTTP on Spark and the cognitive services for big data, and we allow these to be accessible from a wide variety of ecosystems like PySpark as well. And if you're interested, you can check out the cognitive services documentation for more. We have a page that will tell you how to set this up on your own Spark cluster and how to get started using it. And you can also reach out to me at markth@mit.edu or check us out on GitHub. Thanks to everyone who helped out on this project and the Systems That Learn Fellowship, and enjoy the rest of your IEEE Big Data Conference.